The next topic that we're going to be talking about in trigonometry deals with identities. Okay, we've kind of seen some identities in the past, but now we're going to be looking at some more complicated ones. And remember, identities are just mathematical equations that relate two different trigonometric expressions. I know that's a large phrase full of big words, but basically you have some sort of trig expression on the left and some sort of trig expression on the right of the equal sign, and the two are the same, right? The two are eventually equal to each other. One might be a simplified version of the other. One might just, or it may just be that the two, it's nice to interchange between the two for different reasons, okay? So trigonometric identities are what we're going to be looking at. And so to start out, we have some what we call these fundamental identities. And they're sort of our base level identities, and then from there we build off of them along with some other ideas to create some more complicated but yet useful identities. It helps us really ultimately to either evaluate trig function values for angles that we don't already know, things other than your 30, 45, 60, 90 degree multiples. And it also allows us to simplify very complicated expressions of trig functions. So if you have large fractions or sums and differences of trig functions, you can sometimes combine them to get them simpler, to get those expressions simpler. And so that's the reason we're going to be looking at trig identities. So let's first develop a few of the fundamental identities. We've seen most of these before, but I just want to go over just a review of where they come from, kind of briefly, and then put them to practice in some problems. Okay. So the first thing I want to get into deals with a circle. Again, we've seen this diagram before where we put a triangle at the origin, and then you've got your points around the circle that have XY coordinates. The distance from the origin is R, right? The radius of the circle. And so we've seen that before, but now we're going to use that to just kind of review the definitions of the trig functions and then kind of get some relationships going between the trig functions. So first thing is we know that the sine of the angle theta is equal to the opposite over the hypotenuse, which is y over r. We know that the cosine is the adjacent over the hypotenuse, x over r. The tangent is the opposite over the adjacent, so y over x. So we have those three immediately. Then we get their reciprocals, right? The corresponding reciprocals. So the sine's reciprocal is the cosecant, which is r over y. The cosine's reciprocal is the secant, which is r over x. And the tangent's reciprocal is the cotangent, which is x over y. Okay, so these are our 6 trig functions. We've seen all these before. But now what we're going to do is start to relate them together a little bit more. And of course, we have seen all this before, but just as a refresher. Things like the tangent being y over x, right? So think about this. If you were to divide the sine of theta by the cosine of theta, that's an expression, that's a trigonometric expression, right? It's 2 trig functions. Well, that's going to be y over r over x over r. And of course, when you divide by a fraction, you multiply by its reciprocal. So that is y over r times r over x. The r's cancel. You get y over x, which we already know is the tangent of theta. There's going to be a lot of derivations, okay? I call them derivations, where you derive a formula or prove a formula. So you'll see some proofs in this upcoming material on identities, okay, where we prove that 2 trig expressions are equal to each other. Here, I just proved that the sine divided by the cosine is equivalent to the tangent, okay? So what I'm going to do is I'm going to list off, I'm going to keep track of some of these identities off to the side. That way I have some room to work over here. So as a general principle now, the tangent of theta is equal to the sine of theta divided by the cosine of theta, okay? So we've got that as one of our fundamental identities. It's called a quotient identity, okay? In a similar way, because the cotangent is the reciprocal of the tangent, we can flip that fraction and get an equivalent or a similar identity for the cotangent, right? So the cotangent is equal to the cosine divided by the sine, right? And that's because the two are reciprocals, the tangent and the cotangent. We also have what we call reciprocal identities, okay? The reciprocal identities are just that the sine and the cosecant are reciprocals of each other, right? Y over r and r over y, and so we can write them, we can say that the cosecant of theta is equal to 1 over the sine of theta. Okay, that's a reciprocal identity. We can also combine the secant and the cosine. So the secant of theta is 1 over the cosine of theta because they are reciprocals of each other. Let's see. What else? Oh, and then the cotangent is 1 over the tangent of theta. Okay, so that gives us 3 more identities that we call reciprocal identities. Okay, so reciprocal identities, quotient identities, because these are quotients or fractions of trig functions. Okay, now we've also looked at another identity set of identities called the Pythagorean identities. Okay, and where that comes from is, again, off of this triangle from the diagram. There's this. We know that the Pythagorean theorem holds because it's a right triangle. And so you get x squared plus y squared equals r squared. Okay? Well, if you consider starting with the Pythagorean theorem and then just dividing each of those to make some of these fractions, we can create some new identities. So for instance, if I were to divide each of these by r squared, right? Divide by r squared, divide by r squared. Essentially, I'm dividing both sides of the equation by r squared. Then what we're really looking at here on the left is x squared over r squared is the same as, well, the square of the cosine, right? Because cosine is x over r. So this expression is the cosine squared. Y squared over r squared is the square of the sine. So this is sine squared. And r squared over r squared, well, same thing over itself is always 1. Okay. And so you end up with this cosine squared plus sine squared equals 1. We usually actually write that in a different order, and we would say that the sine squared plus the cosine squared is equal to 1. It doesn't matter the order technically, but that's how you're going to see that more often. Okay. All right. So that's sort of our main Pythagorean identity. Also notice, before I jump too far ahead here, just to make a note, the cosine squared, this notation where I square the cosine, it's really the same thing as taking the cosine of theta and squaring its output. Okay, so so basically you're taking a cosine and squaring it. We just write this notation because it's a little bit simpler than throwing a big set of parentheses or brackets around the whole thing every time. So cosine squared or sine squared just means you take the output and square it. Okay. All right. Now, if I repeat this process, but instead of dividing by r squared, let's say I wanted to divide by x squared, for instance. Do that in another color. So if I divide by x squared, divide by x squared, and divide by x squared, we get another set of identities. In this case, we would get, well, x squared over x squared is 1. Y squared over x squared would be the square of the tangent, right? Y over x is tangent, so that's tangent squared. And then r squared over x squared. Well, if you go r over x up here, r over x is the secant, right? So that's going to be secant squared. All right, again, we often write the tangent before the 1. It doesn't really matter the order. So I'm going to write that out as the, try to keep this consistent with my color. Let's go blue. We have the tangent squared theta plus 1 is equal to the secant squared theta. Okay. And then finally, the third possibility is to divide everything by y squared. So divide by y squared, y squared, y squared, and the identity you will end up with is going to be, well, x squared over y squared. X over y is the cotangent, so that's a cotangent squared. Y squared over y squared is 1. R squared over y squared, r over y is cosecant. So it's going to be the cosecant squared, okay? And so this is our third Pythagorean identity. Again, we can construct these based upon the Pythagorean theorem and then dividing both sides by either r squared, x squared, or y squared. And so we get the cotangent squared plus 1 is equal to the cosecant squared, okay? All right, so that gives us 3 Pythagorean identities. We also have then 2 quotient identities and 3 reciprocal identities, okay? These are the main identities that we're going to be using throughout our discussion on identities. These are our main fundamental identities here. However, there are a few other ones that I think are important called the even-odd identities. The even-odd identities really come from, well, I can argue these or derive these a couple different ways. One of them would be using the unit circle and the relationships between the signs, the positives and negatives in each quadrant. Or I could look at the graphs of the functions. Remember that in mathematics, if you have a function that has y-axis symmetry, we call those even functions, okay? And with y-axis symmetry, you end up basically whether you put a positive or negative x value in, the outputs are the same, right? So you go the same height on either side of the y-axis. Could be down, could be up, whatever. So what that means then is if you were to input a positive x or a negative, I should put a line there, or a negative x, whether it's positive x or negative x, it doesn't matter. The outputs are equal, right? So f of x and f of negative x will be equal. The outputs are the same. All right. There are some functions, some trig functions that are even. Okay, they have y-axis symmetry. Namely, let's see if I can get these drawn up. The first one is the cosine. Right? We know that the cosine, when we plot one period of the cosine, it starts up at 1, goes down, and comes back up. Well, if you were to repeat that on the other side, on the left, we end up with y-axis symmetry here, right? So whether you put in a positive or negative value for x, the outputs are the same. If you go over here, the outputs are the same, and so forth. Okay, so there's symmetry around the y-axis. So An example of an even function is the cosine. So I would say that the cosine of theta is equal to the cosine of negative theta. Okay? It's the same reason. So if I input a positive theta or a negative theta, positive angle, negative angle, I get the same output from the cosine. Okay? Because the cosine is even, its reciprocal, the cosine's reciprocal will also be even, the secant. Remember, the secant is a function that has vertical asymptotes wherever the cosine had y-intercepts, or x-intercepts, sorry. And then you end up with these sort of U-shapes, like so. And you can see on the blue graph here the y-axis symmetry again. So the secant is, secant of theta is also equal to the secant of negative theta. That's another even identity, okay? I believe those are the only even identities. Yep, the other ones are all odd, okay? So I'll keep these two. Oh boy, now I'm running out of space. So let me get rid of this, so I'm not going to need it. And I'll write these two identities up off to the side here out of the way. So the cosine theta is the cosine of negative theta. Secant theta is the secant of negative theta. All right, so I got those out of the way. Okay, now we can look at the odd functions, and remember that if you have origin symmetry, you have what we call an odd function. And remember, with origin symmetry, that's where you would, if you input a positive x value, wherever the output is, then if you input the negative x, you get the opposite output. Right, and so you have a reflection between them through the origin, not across the y-axis, but through the origin. Or if you were to put, if I put this point in and it gives me an output over here, then the opposite input would give me a point reflected through the origin right there, okay? So reflections through the origin. Basically, if you put in positive x versus negative x, the opposite inputs result in opposite sign outputs, okay? So we would say that f of negative x is equal to negative f of x, right? So if I have opposite sign inputs, it results in opposite sign outputs. The functions where that occurs are the sine, right? The sine wave. Think about the sine wave for a minute. Sine wave starts at the origin, goes up, down, back up to the origin, right? That's a 0 to 2 pi, but if we go left, it goes down, up, back down. And what you'll find then is that every point will reflect through the origin to another point on the graph, right? This one here will reflect through the origin to another point on the graph, equal distance away. All right, so the sine is an odd function. Maybe I'll just summarize these up on the right here to begin with, so I don't have to rewrite them. So we'd say that the sine of negative theta is equal to the negative sine of theta, right? And I could go through and show you the graphs of the cosecant. Remember the cosecant, I guess I could draw that solid. The cosecant is the reciprocal of the sine, and so it will also be an odd function because it's going to have origin symmetry if you reflect those points. So the cosecant, CSC, of negative theta is the negative CSC of theta. All right, so I've got those two things down. The cotangent and the tangent, if I show you the graphs of those, which we've done before, they also end up being odd functions, okay? So the tangent of negative theta equals the negative tangent of theta, and then the cotangent of negative theta equals the negative cotangent of theta. And I won't go through and show you the graphs, but it's a similar argument. If you plot the graphs, you can see the origin symmetry between them, okay? Okay, so that gives you quite a list of identities, and these are what we call the fundamental identities again. There are 6 even-odd identities, there are 2 quotient identities, 3 reciprocal identities, and 3 Pythagorean identities. And so you're going to need to really be able to use these and know these moving forward as we talk about the more complicated identities coming up. The next video, what I'm going to do is put these to use in some pretty neat examples and work at simplifying things. There's one other thing, but actually before I do that, one other thing I want to mention is that these identities are only actually true when on the domains of the functions. So when they actually exist. For instance, the tangent, this identity is only true where the tangent exists, right? So this wouldn't really work. I guess it does kind of work. When the cosine is 0, the tangent is undefined. And so the equation doesn't really work when you have undefined things going on. So these identities hold true on the domains of the functions, not necessarily for all real numbers, okay? All right, let's look at some examples in the next video.